Welcome back. We have been learning to approximate the area beneath the graph of a function, the area in between, say, y equals x squared and the x-axis. And last week, when we were looking at this, we were building up some rectangles by looking at the y coordinates of our curve. So we've chopped the x-axis into a certain number of pieces. And just to make things easier on ourselves, we've said that each of the rectangles is going to have the same width, and that the height of each rectangle is chosen depending on the formula that defines this function. So in all of these pictures, I might say that we're using left endpoints, and I can just see that in the picture because the upper left corner of each rectangle touches the graph of the function. So each of these rectangles has a height determined by the function evaluated at a particular x coordinate. And I think that these pictures do a decent job showing how our approximation of the area gets better the more rectangles we take. Or you might say the more subdivisions of our interval. Here I am trying to capture all of the area, or at least as much as I can, between x equals 0, x equals 1, and y coordinates between the graph of the function and the x-axis. And I need all of those restrictions in place so that I actually have a finite amount of area to talk about. And you can see, at least in these pictures, I'm always getting an underestimate. That's particular to this problem here. That will be different as we look at different kinds of functions. But I'll have some levers I can pull in here. I can be pulling here. Where do I set the heights of my rectangles? How many of those rectangles will be there? Ultimately, I would like to have, not just an approximation, but the actual amount of area. But besides just saying the area is the area is the amount of paint that you would need to fill the figure, I need a way to definitively talk about this area. What do I even mean by this? Area should be some kind of number. And there's certain properties I would expect area to obey. So we need to really define what we mean by area for these kinds of figures that aren't just simple rectangles, squares, circles, triangles, and so on. We need to take a slightly more rigorous approach to all of this. Here are the same figures again using right-hand endpoints. And for this function, f of x equals x squared, it looks like I'm approaching the same number, though all of these estimates are going to be larger than the actual amount of area here. Now, these have been drawn in using right endpoints. But as I take more and more of these rectangles, the error itself the amount I am off from, quote unquote, the actual answer gets smaller. So in the end, maybe it doesn't matter whether I take left endpoints or right endpoints. And if I think about this, I can make approximations. And as I go further and make more complicated estimates, I should be getting closer to the actual number that I want. And it at least looks from these pictures, there's a little bit to be said about whether or not this process actually pays off for us. It looks as though all I need to do is just make sure that I'm actually taking more and more of these rectangles to calculate the approximation. And sometimes I'll get numbers that are too small. Sometimes I'll get numbers that are too big. But perhaps it's not the approximations themselves that I care about. In the long term, what I actually want is this actual area number, which so far eludes me, but it at least looks very evocative that a number like that should exist. Now, this isn't the first time that we've encountered this kind of problem, where we would like to make some kind of calculation, and we can get as close as we like. We can get approximations that are close without actually being able to just put in x equals 1 or something. And the way that we've dealt with that in the past was the limit. So let's think about how we could use limits for this kind of area problem. Now, on all of these slides, I'm going to be using the lowercase letter n to stand for some whole number. So maybe n is 7, maybe n is 7 million, maybe n is such a large whole number that there isn't enough ink on the planet Earth to write it down. Still be a whole number. It would still be finite, even if that's going to test our idea of what finite means as a concept. Never mind that. So when I'm talking about adding up the areas of a certain number of rectangles, of course, there's got to be a whole number of these rectangles. So I have some interval that I care about on the x-axis, starting at coordinate A, running all the way up to coordinate B. Now I'm going to break that interval down into exactly n pieces. Again, maybe n is 7, maybe n is 7 million. Take your favorite whole number. Now, the formula that I would use to calculate this, the height of the first rectangle should be the value of the function for some specific x coordinate. Maybe I use left endpoints. Maybe I use right endpoints. Well, whether I use right or left endpoints and what the exact number of intervals is going to be, it's kind of hard to write down this formula. F at x1 times delta x, f at x2 times delta x, and so on, ... stopping at f of xn times delta x. I have an intuitive idea about what that formula should mean, about what kinds of things I'm leaving out there in those breadcrumbs. But to help distinguish, I'll be using r with a subscript of n to indicate the right sum using the right endpoints, and ln to be the left sum with the left endpoints. And hopefully, the area itself, this number that I care about so much, or at least the number we are learning to compute, I hope that you care about these things, is going to be the limit of those sums. The limit as n goes to infinity. So whatever number you picked was your number 65,538. Well, too bad, it's still just an approximation of the actual area. Though with such a large value of n, it may well be a very good approximation. So the way that we can agree on what the area actually is, the area is this limit of the sums. So we can just define the area to be this number. The area is the limit of these sums. We can define it first to say it's the limit of the sums using the right endpoints. And for the kinds of functions that we normally care about, so for right now, that's going to be for continuous functions, it doesn't actually matter whether we use the right endpoints or the left endpoints. It matters for any particular approximation, but in the limit, both of those limits will equal the same number, the same area. So limits are our real big idea in calculus. We swept them under the rug a little bit to be working with derivatives for a time, but it's really the limit itself that is the thing that makes this all work. It's the engine that keeps us moving down the road. So here we have another use for it. And now that we're able to talk about this area number, we're going to give it a special name. So there are some technicalities to worry about. I've been talking about, my x1 is going to be determining the height of the first rectangle. My x2 is going to be determining the height of the second rectangle, and so on. Those will be slightly different coordinates depending if you want left endpoints or right endpoints. Sometimes people like to talk about these as the sample points. I don't actually need all the values of the function to approximate its area. I just need the values of the functions in certain places, count them all up, evaluate the function at those different coordinates, see how much area I get. And you can go real in-depth with this. There's an entire art of choosing good sample points if you're in a situation where you can only do sampling. But since this is a class about how great limits are, let's talk about what they get us. So the technical term for what we are working with here is the definite integral. There's a lot of ingredients to this formula. It's kind of a wordy thing to talk about. And for that reason, we have a very compact notation to record all of those ingredients in a small amount of space to save pencil lead. But there is a lot going on here. So when you see this symbol, when I write this symbol, or when you write this symbol too, this one right here, it carries a meaning where every different part of this notation is telling us one of the ingredients for the calculation. The full name of this thing is the definite integral of the function f from a to b. That's the full name of it. I might just call it the integral. Now, this comes in pieces. Reading it left to right, the first thing I see are these numbers a and b. Those are the start point and the stop point for my interval, where I care about how much area is present. These are attached to the integral sign, which looks like a big old stretched out letter S. Fair enough. Inside the integral sign, I have the function f of x that I care about. For right now, it's f of x. For different applications, we might use a different letter as our variable. And so this is followed by, well, it looks like our friend, the differential, dx. And what this x is doing here is telling us what variable we care about. Now, we try to keep functions from getting too out of control in this class, but it's very important that every single integral tells us what variable we care about. And the way that we communicate this information is with the differential right here at the end of it. So think about the integral sign as my open parentheses, and the dx on the end is the closing parentheses. It tells us that this is the whole thing that we are integrating, if you're looking for a verb today. And the definition of what this symbol is, the calculation that I am instructed to follow, is just the limit of those sums from my previous slide. Here it's written a slightly different way. Again, this is using sigma notation as a placeholder because I do not want to write out a very large sum of things. Sigma notation says that my capital sigma here is instructing me to add up a certain number of things. I'll keep a running counter. The I here starts at 1, and for every whole number between 1 and n, we're going to take something that looks like the function f, evaluated at xi, all times delta x. That would be the area of a single rectangle, and the capital sigma here tells me to add them all up. And again, sigma being the Greek equivalent of s, s being for sum. And I like to think of this as adding up all of those rectangles. There's a lot of points, like literally, jagged edges and stuff. The sigma and the delta here are the Greek equivalents of S and D. Just kind of a funny way that the notation ended up getting popularized. So again, these things come with a lot of different vocabulary because, well, frankly, there's a lot of stuff going on in them. Now, I've already said this stretched out S is called the integral sign. If I want to talk about the function itself, right? Different function, different amount of area, that makes sense. In this context, the function is called an integrand, which is just a word meaning the thing that I am integrating. The letters A and B, again, these are some numbers that will get specified when it's time to compute these things. Those are called the limits of the integration. And yeah, that one is a little unfortunate. bit of a double use. We do mean that differently from, calculating a limit. It just means start here, stop there. That's all it's doing. We'd call A the lower limit, and it's very literally the lower of those things in the integral sign. B is the upper limit. And you can ignore what this slide here is saying about dx. I'm calling that the differential. But what this differential does is it tells us what variable we care about. So, a lot going on here. Now, what do I mean by specifying this variable? Well, one of the interesting things about integration is that the actual letter that I use doesn't change anything. If my variable comes with x, if my function comes with x variables, that's fine. I could have the same function written in t variables instead, and I've done that a couple times this term. Or I could write it in some other letter, maybe the letter R, maybe a Greek letter. But each of these calculations would produce the same number at the end. And so I'm not going to get too concerned about exactly how they've been spelled out for me here. And this is a very important note here, that integrals, they tell us the instructions for a very complicated kind of calculation. This is the end result of all of the work we have been doing in our approximations. The integral contains the instructions for all of those approximations and then produces this number as its output. Every integral represents a number. For right now, that number is an amount of area in the xy plane. Later on, in Calculus 2, we'll get to some integrals that represent other things. But those integrals will still be numbers that represent other kinds of quantities. So this was a bit heavy on the vocabulary today. I might recommend you rewind a bit so you can hear me explaining all of these things again. As we go, of course, it's not a very practical operation to be computing these sort of limits for day-to-day work. So very soon, we will find a way to work around it, much the same way as we have developed rules for derivatives. It is not the case that we calculate difference quotients every single time we want a derivative. We have some more powerful tools to work with. Today, we just need to know the integral exists, and tomorrow we will be working with some more effective tools. Not literally tomorrow, figurative tomorrow, but I will catch you later.